Okay, so we can start with today's seminar by Niels Obers. So we are very lucky and grateful to Niels Obers that he accepted to come. So he's from the Niels Bohr Institute and Nordita. Niels has been a pioneer in the field, has been one of the first to realize the importance of these so-called non-relativistic limits. And so it's a great pleasure to welcome him for this first seminar of the course. So Niels.
Okay. Merci beaucoup. Like Marc says, and first of all, let me thank Professor Marc Henneaux for initiating this lecture series on what I obviously consider a super fascinating and rich and interesting topic. And it's actually great to see so many people of the Paris area are interested in it. And from what I understand from Professor Henneaux, there's still really a lot of interesting lectures to come. J'ai habité à Paris il y a beaucoup d'années. Il y a presque 30 ans que j'étais à École Polytechnique. C'était un très grand plaisir et c'est aussi un grand plaisir de revenir ici. C'est aussi un grand plaisir d'être dans les collèges de France pour la première fois. That being said, so things like that I can say in an understandable way, but with the physics, I will now go to English. But let it be said, it's great to be back. So I'm going to talk about non-Lorentzian geometry in gravity and string theory, and I hope that I'm not expecting you're experts in this, but depending a little bit on your background, I hope you go away having learned something, maybe at different levels for different people with different backgrounds. Just want to acknowledge a big set of collaborators that I've been doing some of the work together with that is part of this lecture. So let me set the stage. Often when I speak to colleagues, and I say I'm interested in non-relativistic or non-Lorentzian symmetries and geometries, they consider it kind of exotic. And I hope you will get away seeing my point here, but actually they are not exotic alternatives to good old Einsteinian relativistic geometries that we know lie at the heart of general relativity. But what's really fascinating is that they actually arise in a very natural and controlled way as limits of relativistic physics. And Professor Henneau's beautiful first lecture already underscored a very crucial point to that effect, because, as I've also explained, one of the underlying features of geometry is symmetry, so algebras. And you have precisely seen here in the last 1.5 hours that, for example, Carroll and Galilean symmetries can be obtained in a controlled way from parent symmetries that obey Lorentzian symmetries, like the Poincaré algebra. And maybe it's immediately obvious, so it's not only true for the algebras, but also for the much bigger space of geometries that they appear as controlled limits. This is a very general statement. Now, I'm a string theorist, so what's very fascinating and that I hope to give you a little bit of a feeling for in the second part of the lecture is that such limits that give rise to non-relativistic or non-Lorentzian, I will be in a second more clear what I mean with non-Lorentzian, but such non-Lorentzian limits are actually very natural in string theory, and they are related to scaling near so-called supersymmetric states. They are actually at the heart of the ADS-CFT correspondence. That's a correspondence between gravity theories and quantum field theories, and also matrix theory like descriptions that were quite popular like 25 years ago. Not only that, so they're related to quite well-known things, non-Lorentzian geometries, but they also play a role in interesting and novel generalizations of holographic dictionaries like ADS-CFT that involve Galilean or Carrollian type geometries. This is an intro. I'm going to explain for you what Carrollian and Galilean geometries are, to give you a feeling and a definition, well, more than a feeling of what they are, but just to set the stage. And so related to these points, I just want to underscore, and for me it was sort of, well, you should always be careful with the word epiphany, but a little bit of an epiphany that if you have not the right glasses on and you do some limit of your favorite geometry, say the Schwarzschild geometry, the black hole geometry in GR, in certain limits you find that the beautiful metric that describes that geometry, say Schwarzschild, becomes degenerate. Now, so I cannot speak for others, but I have lived in an age, actually for many years during my scientific career, that I detested these limits where the metric became degenerate and thought, now I'm into the realm of having an ill-defined geometry. But here comes a very interesting thing. Precisely what you think is ill-defined becomes well-defined if you enrich your mathematical framework and tools. So as a slogan, you can say non-Lorentzian geometry makes well-defined what you might think is ill-defined, but very well-defined on the same mathematical rigor. And roughly, just to evoke an image, just in general relativity, the whole space-time is beautifully described by a single object, the metric. You just have to be willing in these non-Lorentzian geometries to accept that you don't have your space-time description anymore in terms of one object, but a separate temporal and spatial structure, but still being nicely covariant and so transforming in a nice way under coordinate transformations. And precisely the simplest cases of that I will introduce you to are Newton-Cartan and Carroll geometry. They are geometries that precisely realize, in a sense that I will make more precise, the symmetry algebras that Professor Henneaux has just derived for you from this beautiful classification. Yeah, and then to expand on this point, it just turns out that if you, and then for this you really need all the ingredients, the richness of string theory. You need the fact that string theory has strings, also the fact that string theory has brains. And that actually turns out that string theory very naturally produces such non-Lorentzian geometries, and in fact some very interesting stringy or brainy generalizations. And just to give you a little bit of an idea, like in this classification, Professor Henneaux separated time and space, right? It was very important. Yeah, the zero coordinate for time and vectors for space. And time is temporal, and the space is spatial. I will show you also in equations how that generalizes, that notion generalizes for branes, is precisely that we have to extend what we mean with temporal. Temporal becomes now multidimensional, but it has to do with the longitudinal directions on the brane. And whatever we think of spatial has to do with the transverse directions to some extended brane-like object. And then it so turns out, and hope to have some time to show you, that so-called near BPS decoupling limits, and I will explain what that is, it has to do with supersymmetry, they actually force space-time to become non-Lorentzian. So it's also something intimately connected to supersymmetry, in fact. So I hope just these words already, I think, for many experts would sort of highlight, hopefully, that it's far from exotic, but very relevant for even mainstream applications. So actually there has been quite a progress in understanding non-relativistic / non-Lorentzian corners. terminology Professor Henneaux commented already on, in a wide domain of fields, field theory, so gravity and string theory. I mean, they are of course related, but just in field theory alone, you can do very interesting things by considering these non-Lorentzian corners. And all that recent progress, say from the last, well, more than 10 years, builds in large part on an improved understanding of what these non-Lorentzian geometries are. Now I'm going to reveal for you the logic behind the word non-Lorentzian, and I could not agree more with Professor Henneaux that defining something by what it not is not ideal, because the complement of something is quite big, if not infinite. But but it's at least a little bit better than non-relativistic, but non-relativistic is also very bad. But as I will make clear, it's space-times with local symmetries other than Lorentz symmetries, as you have in GR, the Lorentz. Now, non-Lorentzian geometries, just to show you the breadth of it, and this is not even exhaustive, but just to give you an idea. So in the last 10 years, they've shown up in covariant formulations of the post-Newtonian approximation in general relativity. General relativity is very hard to solve. You have to make approximations. That's precisely an approximation, the post-Newtonian, in which velocities are small compared to the speed of light. And to do that covariantly, non-Lorentzian geometry is a very nice tool. That's also shown that there's actually that non-relativistic, in the sense of speed of light to infinity limit, the non-relativistic limit of gravity is richer than Newtonian gravity. I'll comment on that in passing too. But it has revealed sort of a strong non-relativistic gravity regime. Then they appear in holography. I've already said a lot about that. Beautifully, they also appear in cosmology, black holes, horizons, and singularities. Just to the picture you can keep here is, as I said, it's very interesting, precisely in a sort of extreme regions of a space-time, like for a black hole or for other space-times. With the extreme, I mean very far away at asymptotic infinity, or close to the horizon, or for that matter, in the singularity. There, before, well, I at least 15 years would have said, that geometry is singular. Precisely in such extreme regions, the geometry becomes non-Lorentzian. So it's exactly ubiquitous in interesting solutions that, of GR, and that play a role in our description of the universe. Maybe not so surprising, and this was sort of a big motivation of the development in the beginning, sort of 12 years ago. Of course, like an area, a field of research where you would expect non-relativistic limits to be especially relevant is, of course, condensed matter systems. And indeed, in there, they have had some very interesting applications, also in some topical things like fracton physics and the fractional quantum Hall effect. Even now, and this is not just name dropping. I myself have written some papers on applications to biophysical systems, and other people too. So you can even apply this machinery to blood cells, for example, to red blood cells. And then last but not least, I just like to mention there's also the more like pure mathematical aspects that have interested people, and in fact also I know there are some philosophers that have become quite interested in these non-relativistic limits, because it precisely shows also that there is some kind of gravity theory between Newton and Einstein that has been overlooked, and how does this fit within the bigger picture. And then this is not the motivation of the whole talk, but I just wanted to show this cube of physical theories, how it naturally gives you the question about non-relativistic symmetries. So this was part of my motivation, and maybe in the talk you will see some partial answers to this. But I find this always inspiring, especially for people who have not seen it. It becomes boring if you have seen it too many times. But this is the so-called Bronstein cube, a cube of physical theories. It's not complete, but it gives you a very nice anchor to look at the different theories or theoretical frameworks that we have in physics to describe nature. And it's based on the fact that there are three constants of nature, h bar, Planck's constant, Newton's constant g, and 1 over the speed of light, c. I write 1 over speed of light because then that becomes 0 if the speed of light goes to infinity, and that's a Newtonian limit. Now, I don't want to go, through all these corners. Here's classical mechanics. Well, quickly, so this is the relativistic world, the upper side of this cube. Here, this is here's 1 over c. This is the relativistic world. This is, because h bar goes up, is the quantum world, and the front face here, g, is the gravity world. Okay, there you can have all combinations, and this is also pretty much all the courses we give in our physics department. Quantum field theory, special relativity, GR. Quantum gravity is the theory where you have to take into account the finiteness of all these constants of nature. I put here /string theory because I like the string theory approach and find it very compelling. But now here too, I just want to focus on these two corners that are seen from this point, seen from the GR point of view and from the quantum gravity point of view. They are the non-relativistic, the large speed of light limits of that. Let me first start with this. I have drawn this cube many times when I taught GR. And without blinking, I have put here Newtonian gravity. I think most people would do that. But actually, one of the things that research in the last years has shown that already that there is something more general than Newtonian gravity, that includes Newtonian gravity, that has non-relativistic symmetries, and that you can precisely uncover by using Newton-Cartan geometry that I will introduce in a second. So that's already interesting, shows that even classically there is actually some gravity that is, like I always like to say, in between Newton and Einstein. The crucial thing is that for the people who have done a GR course, to get Newton's theory from GR, you also assume weak fields. But that assumption doesn't need to be there. That's why it's strong non-relativistic gravity. But having convinced that there is, well, even if it was Newtonian gravity, but this raises also the question, is there some perhaps simpler version of quantum gravity that's non-relativistic quantum gravity? Because actually the way this holy grail point is most often approached is saying, we understand quantum field theory. Let's add gravity to this. Or we say, we understand classical gravity. Let's quantize it using what we have learned from quantum field theory. Of course, there are various challenges here. But sort of the one thought was, if you can understand this better, then maybe there's also a way to have like what I call a third route towards quantum gravity. So that was also a motivation, and precisely sort of to understand both the classical and quantum corner uses some version of Newton-Cartan gravity, and also it raises precisely the question, how does this all fit with string theory? For example, if you, like me, are a string theorist, is there also some string theory here? And at the very end of this lecture, I will show you, yes, there is a consistent, ultraviolet, complete corner of string theory that you can put here. So this is, I think, very motivating, this cube. It's very important to say that the cube is much richer than just these 8 sides in some sense, and also, you can with each direction you can go to the direction where the constant becomes 0. But a very obvious question is also, can I go the direction where the constant becomes infinitely big? So this would be the small speed of light, precisely the Carrollian limit here. It would be here, so the strong coupling limit of quantum mechanics, where it's non-perturbative, and the strong gravity limit. So that actually suggests that precisely besides the standard large speed of light limit, that again is often called non-relativistic, there are many other interesting corners in the space of physical theories. Small speed of light, we've heard about it already. More general limits in string theory, which are actually directly related to vanilla non-relativistic physics by dualities. And then here's a technical point that I will only spend one transparency on, but just to make you aware, maybe the younger generation of PhDs that maybe want to think more about this. There is a subtle difference. If you take some parameter, like the speed of light, the subtle difference in the limit, sending c strictly to infinity, and doing a large speed of light expansion. You can ask me in the end. Yeah. But so there's a subtle difference. I just want to flag that. But the common feature of all this is that you get space-times that are described by some type of non-Lorentzian geometry. And these non-Lorentzian geometries, they show up in different interesting physical incarnations. And the main ones are these three bullets here. One is as, and again, I will give examples of this. One is as the background in which certain probes live. This sounds very fancy, but I'm just saying, as an example, a relativistic particle moves naturally in a relativistic space-time, in GR, in a pseudo-Riemannian geometry. Likewise, a non-relativistic particle is a probe of Newton-Cartan geometry. So that's what I mean with this. Then I mean, with the second bullet, I mean that, again, everything is parallel with what you know from Einstein's theory. Just like Einstein's theory is the theory that tells you what's the dynamics if I have a space-time, if I let it fluctuate. So what governs the shape of space-time? So that's, for Einstein's theory, the Einstein-Hilbert action, or the Einstein equations, which are the equations of motions of the Einstein-Hilbert action. And that falls under the name, I call that dynamical geometry. So likewise, as soon as you have discovered a non-Lorentzian geometry, you can ask yourself, what is the corresponding dynamics that describe its fluctuations? So what's the analog of the Einstein equations? And then last but not least, this is maybe very much for experts, but I said that you could also have extended probes, like brain-like objects, probing some non-Lorentzian geometry. Then well, it's a typical case of like whatever you can think of happens in physics. Then it can also happen that the probe itself probes a non-Lorentzian space-time, and in addition, the probe has a non-Lorentzian symmetry on its wall volume. So there can be sort of double non-Lorentzian features. And this is quite generic in string theory, in fact. Okay, after this rather long outline, I give the outline. I want to spend some time on now, gives you what is non-Lorentzian geometry, and illustrate this by giving you an idea what Newton-Cartan and Carroll geometry is. And then in the end, I can already see, and it doesn't matter, I have to skip some rather technical slides, but it doesn't matter, but I will give you a feeling of the application of non-Lorentzian geometries in string theory, but highlighting the main points. But maybe this is a good time to pause for possible questions. let it also be said that, don't hesitate to ask me a question. I'll try to be alert and see fingers pointed up. But okay, you're probably thinking, now the speaker has been using the word non-Lorentzian like a million times. Show me what it is. So I find this the easiest to sort of heuristically first make clear by underscoring this very important notion that you can just formulate in words, that the local symmetries of space and time are one-to-one in a certain sense, a certain precise mathematical sense, to the geometry of space and time. I mean, and that's also why Professor Henneaux started with symmetries. I mean, you have to understand symmetries before, in my world, before you can talk about geometry. And then here was maybe a little bit poetic with words. I call it space-time symmetries. It would be more correct, but I don't do it because normally there's not such a nice lecture on kinematical algebras before my talk, but I should actually put here kinematical algebras. You could see that there was a common feature of all this, right? There are time translations generated by the Hamiltonian, space translations generated by the momentum, and spatial rotations generated by J, right? Angular momentum. Just for ease now, because you might ask me all kinds of questions about ADS and the Sitter extensions, but let's keep it simple. Let's say that's I call it for now, for simplicity, my bare bones symmetry. In fact, that's the symmetry that your last one in the list has. I forgot what the number was, but it's also called the Aristotelian algebra. So where you only have the rotations. And a crucial difference, again, that you could see in this classification is what type of boosts you augment these bare bones space-time symmetries, namely translations in space and time and spatial rotations with. And of course, there's more, but let's focus on this crucial thing, type of boost. For people who know relativity, there is the relativistic or Lorentz boost that mixes time and space, like this, right? And you see here the speed of light. So that's one boost. It's also in this algebra. Now the Galilean contraction, I'm actually doing the same as Professor Henneaux here, but now at the level of coordinate transformations. The C to infinity limit precisely reduces these Lorentzian limits to the Galilean symmetries, in which time is absolute and space is relative. And the other more esoteric but very interesting limit actually is the speed of light to zero limit, in which space becomes absolute and time becomes relative. So these are, for now, the kinematical symmetries that I want to confine myself to for simplicity. And you have seen part of their derivation in the previous hour. And just to say, so in Lorentz, you have nice 45 degrees light cones. In the Galilean limit, these light cones open up. Contrary to that, in the Carroll limit, these light cones close up. So here, everything is causally connected because the propagation of signals goes infinitely fast. Here, you could say, is there anything interesting in physics in it? Because, I mean, the whole dynamics is squeezed to time. So, it looks like, and you can only move in time and not in space. That sounds kind of boring, but interestingly enough, there are some really deep physical applications of this. But that's how the light cone looks like in these cases. And then precisely, there is a mathematical way, and I will spend one transparency on it, but that enables you, given the local symmetries that you want your space-time to respect, produce a geometry that implements those local symmetries. So precisely pseudo, the pseudo is there because we have time. Pseudo-Riemannian geometry does that for the Poincaré symmetry. That's GR. And with that, you can show that space-time in GR is described by a metric, G mu nu. And this is the line element. Now, Cartan, and yeah, I find this really very deep and brilliant. Already some years, like I think it was 1923, so pretty shortly after, 1923, after Einstein, he realized something that I think, yeah, well, that I dare to say, I cannot speak for other people, but I did not realize when I started teaching GR, and I might have actually said some wrong things, because, you know, the slogan is always, we hear like, oh, Einstein, he geometrized gravity, and you know, and that's the and that's GR. That's but I mean, both is true, but not the and that is. Yes, he geometrized gravity, but he did it with sort of an Einsteinian bias, a relativistic bias, in the Einsteinian way, or in the Lorentzian way. He geometrized it, but precisely wanting that the local symmetries of space-time were those of his theory, special relativity, right? He wanted the local symmetries to be Lorentz. So that's what Riemannian geometry does. Now, Cartan was so brilliant to realize there's two different things, geometrizing it and what symmetry the geometry has locally. So he realized Newtonian gravity can also be geometrized. I just need a geometry that makes that implements local Galilean invariance, and that's then another geometry, and that is what Newton-Cartan geometry essentially is. So so just like Riemannian geometry is like patching together pieces of flat Minkowski space, because locally on points. Newtonian geometry is patching together pieces of flat Galilean spacetime, or Newton-Cartan spacetime. That's why the breadths are here, because this is my picture for flat Newton-Cartan spacetime. In some sense, it's each slice, because time and space are on a different footing, each slice represents a particular time. That's flat Newton-Cartan spacetime. But you can make some ciabatta from this, you know, by just pressing it and curving it. But this would be then like a curved Newton-Cartan geometry. So it's all about, said in another way, what I just said, what type of equivalence principle do you incorporate? Einstein likes freely falling observers to see the laws of special relativity. That was his relativistic bias. It's okay. Cartan realized, oh, I can also want that freely falling observers see Galilean relativity. And then you get Newton-Cartan geometry. Now, what is it then actually? It's still described by tensors, just not, and tensors are for the experts or the people with more like mathematical physics background, that transform nicely covariantly under coordinate transformations. It's just not one object, G mu nu, anymore. But in Newton-Cartan, the geometric data are a clock form. It's an object with one index and one form. A spatial metric, or rather inverse metric. Some object here that enables you to measure length. And a vector field, mu. And I should say tau and h are orthogonal. So tau, I mean, your time is a zero eigenvalue eigenvector of this spatial metric. So this spatial metric, as a tensor in space-time, is in d dimensions is rank d minus 1. But you know that's also logical because there's time and there's space. So this will be a non-invertible object. And there's also a vector potential, and its origin I will explain better in a second. That is in a sense, in a nutshell, a covariant way to encode the Newtonian potential. Very importantly, in Newtonian gravity, and this is also what Cartan assumed, time is absolute, right? And in a fancy way, you can phrase it like this equation. It says that the one form tau is closed. So that's a condition on tau to get Newtonian gravity. And with that condition, Cartan could show that you could write Newton's equation in a covariant form like this, where R bar is some appropriate Ricci tensor constructed from these data here, using some connection. I'll say a little bit more. But so, and I hope this is not a mystery anymore that you can geometrize Poisson's equation, because the geometrization aspect of it is just the fact that we have diffeomorphism invariance, that the laws of physics should take the same form independent of coordinate transformations. And that fact is there whether you're a Newtonianist or an Einstein person. That just more as a side remark, it's obvious what I'm saying to experts, but I find it very interesting that, and it's really obvious, but I think it has misled many people, including myself, that we were very unlucky that Newton wrote down his law of gravity in an accelerating system. That has really screwed at least me up for decades. That's a very anthropocentric point of view, right? Because we are here in an accelerating system, because we're accelerated upwards. We know, thanks to Einstein. But if that weren't the case, I think we would have found many of these things before. But okay, we cannot blame Newton. Yeah, it did great work, of course. So here's the picture again. Just some, now, one thing is I give you symbols and say, instead of the metric, you have tau, m, and h. I should also tell a little bit more about it, maybe. I'm giving here the relations of orthogonality relations and completeness. So there is a vector orthogonal to tau that's, so your time-like, one form has also a time-like vector orthogonal to it. Yeah, there's objects with indices down and indices up, and they satisfy this completeness. But importantly, where is the Galilean symmetry? These objects transform in a certain covariant way under local Galilean boosts. So if you have a boost parameter, this is a fancy way of saying it's space-like, because this contraction with the time-like vector is 0. So for any space-like boost vector, so as many parameters as you have space, this is how these objects transform. And tau down and h up are invariant. You can derive that. So that defines for you the geometry, or well, the analog of the metric. Then to start doing gravity, you have to define further notions on this geometry, namely define a connection. So how can you take covariant derivatives? Then there's a very nice analog. This is a little technical, so I will not spend too much time, but just to make it a little bit more real. There's an analog of metric compatibility, so a covariant derivative of tau and h being 0. In GR, that's the covariant derivative of tau of g equals 0. And you can get a connection, and that connection is not necessarily symmetric anymore, and precisely has torsion when we go beyond absolute time. So apart from all these equations, I just want to, the main takeaway of this, beyond the technicalities, is that Cartan, because he was so focused in 1923 on getting Newtonian gravity, he from the outset demanded absolute time, so no torsion. It so turns out, and this is in part what started a lot of these developments, that in certain setups, well, I stumbled upon it through non-anti-de Sitter holography, so through string theory settings, it's very natural and important to have torsion. So that sort of made this revival to realize, yeah, you can require absolute time and have no torsion, but there's a very important generalization that has torsion. And in fact, it's also this generalization that has torsion that corresponds to the strong non-relativistic gravity regime that goes beyond Newtonian gravity. So torsion is important, but I will not, it's more than a technicality, it's also something conceptual, but I will not spend more on torsion, even though it's underlying many applications. Now maybe, okay, I'm not staying this technical, but I just couldn't resist, again, for maybe more of the experts, since you have seen interesting kinematical algebras, the more precise relation between geometry and algebra. That's on this transparency. And I wanted to illustrate that for Newton-Cartan geometry, which we're now talking about. So first of all, what is the underlying symmetry algebra of Newton-Cartan geometry? I might have given you the impression that it's Galilean, so the one we have seen in the lecture before. But it's precisely an extension of it that Professor Henneaux mentioned in the last minute. It's not quite Galilean, it's the Bargmann algebra. So remember the last lecture, I use G, but Professor Henneaux uses K, but that's the same. So, and JAB is this J. That's Galilean, and we have seen the algebra many times. In particular, the commutator of H and the boost gives translations, and in particular, it's behind the screen here, translations and boosts are zero, but there is an extension of this, so-called Bargmann extension, that places here a non-trivial generator, n, which is a central extension because n commutes with everything here, but it appears here. Interestingly, and I'm not going to show you the algebra for it, but it's nice you have heard and seen the method. This algebra with this mass generator can be gotten from an Inoue-Wigner contraction, but not from Poincaré. You can just count. There's not enough generators, right? Poincaré has 10, and the Bargmann has, in 3 + 1 dimensions, 11. But you can actually get it from Poincaré times an extra U1 generator, sometimes an extra commuting generator. If you take that bigger algebra and do an appropriate Inoue-Wigner contraction, you can get this Bargmann algebra. Okay, this sounds all very like why you're doing this. There's of course a very important physical motivation why we think about non-relativistic in the sense of large speed of light limit physics, why the Bargmann algebra is important. And that's the important fact that in non-relativistic physics, mass and energy are not the same anymore. I mean, so we all know the slogan E is mc squared, but that's Einstein. Energy and mass are related. But in the Newtonian world, mass and energy are two different quantities, and they correspond to two different generators. In fact, the energy corresponds to H, the mass of some Galilean particle corresponds to the generator, and that's why it's there physically. How to see Newton-Cartan geometry originating from the Bargmann algebra? Okay, that's in a sense the mathematics of making precise how to incorporate locally the Bargmann symmetries. This is for aficionados. For that, you have to gauge that symmetry. That means you introduce a gauge field that takes values in this Lie algebra, H, P, G, etc. And the gauge field components for each Lie algebra, you give a name like this. And then I just state, without a result, but just to give experts or, well, maybe more PhD students a feeling. The things I've just shown you, tau, h, and m, they are precisely these, correspond to these gauge fields in this Bargmann valued gauge connection. So tau is the gauge field corresponding to energy, E is the gauge field corresponding to translations. If you square it, you get h. And the M field is the gauge field corresponding to this mass operator. And you can really derive, using the algebra, that the gauge transformations reproduce the transformations on the local Galilean boosts and other local transformations that I gave before. So that fixes for you the geometry and its symmetry properties. And now you can also understand that you can, in principle, do this for any kinematical algebra. And there are also many generalizations of this. So these are kinematical algebras based on that are relevant for particles. But there are also kinematical algebras that are relevant for extended objects. So you can see the whole richness now maybe already in front of you, that we just have a procedure to take some kinematical algebra, gauge it, and we get a geometry. But of course, we'd like to have some motivation to do it, and that maybe comes later. One thing is to have the geometry. The other is, like I said, we would like maybe then to know how do relevant particles couple to that geometry. So here I just wanted to explain to you the coupling of a non-relativistic particle to T and C stands for torsional Newton-Cartan geometry. I'm a little bit militant that it's very important that there could be torsion, otherwise it's sort of a subset of the geometry. But you can also just read NC, Newton-Cartan geometry. Just to tell you, it's interesting to know and actually has also deep physical implications. There are actually two routes, probably there are more, but two routes that I find nice to explain to get such a coupling. One is a little bit more abstract, and I will not dwell on that, but just say it as a buzzword. You can go to one dimension higher than you are in, because suppose I want to know how a non-relativistic particle in 3 + 1 dimensions couples to 3 + 1 dimension Newton-Cartan. You can go to one dimension higher, 5 dimensions, and do a procedure that's called a null reduction. Essentially means you identify some extra compact dimension, but it's very special compact dimension because it has 0 length. Okay, and there are all kinds of ways to make this well defined. But if you do that and reduce to 4 dimensions, then you can get the action. So there you just start from, say, gravity in 1 dimension higher, but you do a null reduction. A more direct way, because you could also ask, can I just be in 3 + 1 dimensions and take a large speed of light limit of a relativistic particle? So that's the way I wanted to illustrate here in a second. So now it turns out to get a nice, well-defined action without infinities. You cannot just start with a particle and take the large speed of light limit. Essentially, well, or you have to just close your eyes and kill an infinity. Essentially, if you do that, and many people in the room might have seen it, it's obvious. If you do that, you take the non-relativistic limit, you get an infinity, because any particle, relativistic particle, would have a rest mass, mc squared. If c goes to infinity, that goes to infinity. Then you can say, okay, I just, that's just a constant, so I take it away. But for various applications, especially when we couple to gravity, 0-point energies matter. So here's a nice way to not get an infinity, but to cancel the infinity and have a very well-defined limit that gives the coupling of a non-relativistic particle in Newton-Cartan. So what you do is you take a relativistic particle, but that is charged under electrically charged under a Maxwell field. So you actually force yourself to consider GR together with Maxwell. It's called Einstein-Maxwell. And not only that, you require, you insist to make it work, that the particle is extremal, and that means essentially that it's in appropriate units, its charge is equal to the mass. So then the action is this. This is the coupling to electromagnetism. Now you implement the limit. Okay, some details, but so we implement this limit in curved space-time. So you have to make a well-defined large C expansion of the metric and of this gauge field. But you precisely see that the infinity caused the mc squared that sits in here can be cancelled by letting this electric field blow up. We call that a critical electric field, because that will cancel the infinity, and then what remains is this action. And actually, we have one of the fathers of this cancellation in the audience who saw this very nicely for D-branes and strings, in fact. But there already you see that it's very natural in string theory. Here I'm just getting out of the air. Well, I'm just showing how you can do it, a method. But this is a very nice covariant action, right? And you see the background geometry, m, h, tau. And this has the interpretation of kinetic term, and this is the coupling to gravitational potential, the potential term. This is actually, and I can already see I don't reach it in much detail, but for the string theorists that know that string theory has actually precisely particles in the spectrum, superstring theory, with this property, like I don't have to invent such particles with q equals m and that are charged. Namely, string theory has d0 particles that are precisely BPS, meaning the charge is equal to the mass. They are precisely charged under a one form, under electromagnetism. So, and this limit that I described here is actually nothing but the Banks-Fisher-Schenker-Susskind limit of the late 90s applied on d0 particles. That gave us so-called matrix theory and gave us a non-perturbative definition of M theory. So here you already see BFSS is the non-relativistic limit. That was, of course, known 25 years ago. But what was not known 25 years ago, all this was done in flat space time 25 years ago. Now we know that the d0 particles in the BFSS naturally probe Newton-Cartan geometry, in fact. And it follows very naturally from the near BPS limit. And consequences of that are being investigated as we speak. So it's really, so we're revisiting this BFSS dynamics in view of the underlying non-Lorentzian structure that these d0 particles probe. Just to underscore how natural Newton-Cartan geometry is as the background geometry for non-relativistic field theories. In fact, if you write it like this, and again, I've talked to many condensed matter physicists and other people around it, that this has not been realized, I don't know, 10 years after Einstein in condensed matter circles. It's just, I think there's a direct consequence of communities not talking to each other, because anybody growing up doing particle physics, string theory, quantum field theory knows a relativistic quantum field theory can be covariantly coupled to a pseudo-Riemannian metric, and precisely the stress tensor is the stress tensor of the theory is the response to the variation of that metric. And again, why does relativistic matter naturally couple to G mu nu? That's because relativistic quantum field theories have global Poincaré symmetry. So if you want to make that local, then the corresponding geometry is G mu nu. Then very naturally, and again, it surprises me that this has not been realized before. One of the pioneers of this realization was Damson, 2013. Was, in condensed matter, we play around with many, often 2 + 1, that's why there's a 3 here, but it works in any dimension. But they play around with many non-relativistic quantum field theories. They have global symmetries, non-relativistic symmetries, like Parkman. So the natural geometry to couple those two is precisely the geometry that makes that a local, i.e. Parkman symmetry. And then you get a very beautiful way of how you can compute in non-relativistic theories the energy current, the spatial stress, and the mass current by varying with respect to the appropriate background fields. This also clearly shows, right, you need an M field, right, because mass and energy current are not the same in a non-relativistic field theory. So you can derive this very nicely from the Noether procedure. It can give rise to word identities and has actually been used quite ubiquitously as an organizing principle for effective theories and hydrodynamics. And of course, you can do many analogs of this, and in fact, for many other cases. Very quickly, just to give you an idea, I explained for you, and I hope you saw the highlights of how to get the probe action of a non-relativistic particle, in Newton-Cartan. As I emphasized in the beginning, there's also the dynamical aspect. You can ask, what is the analog of the Einstein-Hilbert action for Newton-Cartan geometry? And here's a nice way to get it. It's quite important. Well, so this is the dynamical analog of the fact that you have to take the large speed of light limit of a charged relativistic particle with extremal charge. The space-time dynamical analog of this is start with Einstein-Hilbert and Maxwell. Do the limit on the geometry. This is relativistic, and this is the large. This will implement the large C limit. Details are not so important. But the crucial thing is, again, a priori you get an infinity. But by tuning the Young-Mills coupling constant appropriately with Newton's constant, you can cancel the infinity and be left with a finite part. That's the essence of it. So, two things I want to say here. Well, first of all, there exist actions like Einstein-Hilbert. They look a little bit more complicated, but the geometry is richer. But that describe gravity with Newton-Cartan symmetries. This is roughly the spatial curvature. Here is some acceleration part, and here is some coupling between torsion and the field strength of this M field. What I wanted to just mention here in passing also, again, for the string theorists under us, note that I made a divergence cancelling here by just postulating that the Young-Mills coupling constant is aligned or related to Newton's constant. Again, what's very beautiful in string theory, we don't have to invoke that principle because in string theory, this coupling is the same as, let's say, for D0 branes, but for everything, Well, in string theory, it's built in that the coupling to gravity and to the matter fields is the same strength. And that causes this cancellation to happen naturally in string theory. It's quite crucial. I skipped this just to say you can also do the dynamical part using the null reduction part. Maybe interesting to say, apropos symmetries, you can actually prove, it's not so easy, but you can prove that this action is the unique two-derivative action that has Barkman symmetry. Just like Einstein-Hilbert is the unique one with Poincaré symmetry, two-derivative. It was actually surprising that there's this other way with the null reduction. Looks very different, but then you can use some amazing identities and show that it's the same. But that's more like a technicality. Good, now we come to Carroll. Once you have understood the sort of the name of the game, and I don't know how many of the details you have followed, but I try to be quite extensive for Newton-Cartan geometry, namely showing you the algebra and sort of how you can gauge it and various other properties. Then Carroll geometry actually follows from the same principles, just using another algebra. Just using the other beautiful algebra that Professor Henneaux showed. Just to remind you what was different with Carroll, Now suddenly, and okay, I use here now C, but the C is now the K here, but then for Carroll. Now suddenly P and the commutator of a translation and a Carroll boost commutes to the Hamiltonian. It was there many times. This was PK equals H commutator. Incidentally, the Carroll, there's a little asymmetry you can maybe already see, right? The Carroll algebra has as many generators as the Poincaré. Again, it's obvious, right? 10. Just like the Galilean has as much. But Galilean is a little bit special that it likes to have Barkman. This is not a mystery. This is because the regular non-relativistic world that we live in has massive particles. But actually, pure Galilean is also relevant if you're interested in massless Galilean particles, even though that sounds like a contradiction. But okay, that aside. Back to Carroll. So you can again, for example, gauge the Carroll algebra with the same method. Now you introduce a Carroll Lie algebra valued gauge field, and you'll find that the geometrical quantities that are Carroll boost invariant are a time-like vector field and a spatial metric, like so. And okay, so this is Carroll boost invariant. This inverse H transforms in a certain non-trivial way on the Carroll boost, and that defines for you the analog of the metric for Carrollian geometry. So it's a little bit, it's in a sense dual to Newton-Cartan. In Newton-Cartan, the basic objects are tau down and H up. They are boost invariant, and here it's just the opposite. Now it's the vector field that generates the time direction and the metric on spatial slices. I said it can be defined intrinsically, gauging the Carroll algebra. I'm not going to show you the formula. But it can also be obtained from a small speed of light limit in general relativity. I think, as Professor Henneaux already said, this is just to flash that, you know, and I just, these references are not complete. They were maybe complete 3 years ago, but so they were complete 3 years ago, but then it's these references and 150 more that are relevant. but here I just, with some buzzwords, wanted to highlight why Carroll is interesting, and that it sort of pops up in various partially interrelated, partially non-related areas. I actually like to start with this bullet because, in a very visionary paper, and I say that in a way that I honestly mean, in 1979, Professor Henneaux actually considered the Carroll limit, the speed of light to zero limit of GR. That has been very inspirational, but so has been a revival precisely looking at that in recent years. So just as a pure interesting other limit of GR, that's quite interesting. Actually, in the pure limit, GR becomes a very nice theory because of its ultra-locality, because the light comes close up. The partial differential equations become ordinary differential equations. And you just have propagation. It's also obvious, but just propagation at each point on space in time. So it becomes ordinary differential equations. But then as a new limit to expand around, I think its potential has not really been used yet as a new method to expand around and find interesting approximate analytic behaviors. I think there's still something to do there. I do it a little bit in random order, but one of the ways that I got interested in it was actually in its application to inflationary cosmology. Actually, precisely, you know, we have a cosmological horizon, and precisely when you go super Hubble, the region of going super Hubble is precisely a Carrollian limit. So that can explain some structures in cosmology. But very importantly, Carrollian geometries appear naturally on null hypersurfaces. And we know of some really, and incidentally, this is an example of the general point I made in the beginning, that precisely in extreme regions of space-time, where we normally say, there's something degenerate happening. Yeah, degenerate from the GR point of view, there interesting non-Lorentzian structures appear. And the particular non-Lorentzian structure that appears on null hypersurfaces is precisely Carrollian. We have null hypersurfaces on black hole horizons. We have them at future null infinity in asymptotically flat space-times. That's why it's believed that quantum field theories with Carroll symmetries might play a role in flat space holography. And that brings to the second point that there's a very interesting extension of Carroll, namely a so-called conformal extension. I heard that this will be also one of the lectures of Professor Henneaux in the future. Very important topic, and it's the BMS group. So, so here, these Carroll symmetries, or rather conformal Carroll symmetries, play a very important role in the most recent developments of understanding holography for asymptotically flat spacetimes and relations to the so-called celestial holography program. Then last but not least, because I didn't even mention string theory yet, then there are hosts of string theories that have some type of Carroll symmetry. I don't want to snow you with details, but there are now string theories that have Carrollian symmetry in the sense of that the space-time they probe has Carrollian symmetries. At the same time, there are also string theories that have Carrollian symmetries in the sense that the Wold sheet theory of the string has a Carrollian symmetry. Those are two symmetries, different symmetries. So that's a very active area there where the last thing has not been said and done yet. Then and this is one transparency just to give you an idea. Because I said at the beginning, even though it was sort of technical, that there's a little bit of a distinction between taking limits and doing expansions. One of the things that I have worked a lot on, and in fact, well, the paper of Professor Henneaux of decades ago, the same approach, is really more like start with GR and reinstate vectors of C and start to do a large or small C expansion. Okay, then it has a leading term and a subleading term, and etc. But that's slightly different from taking the symmetry algebra, taking a certain large C limit, and then asking what's the geometry. This is a sort of more a way that directly connects to GR. It's also very rich and has some subtle differences that I will not go into, but they actually are. But just to give you an idea, what you do is you reinstate vectors of C in the natural physical way. You write your metric. This is a time-like field bind. We're still relativistic. This is a metric on spatial slices, and T is proportional to pi. We didn't do anything here. Well, but we didn't break relativity yet. We just invented two different symbols for a time-like direction and a space-like direction in GR. But you should see it. I always like to say you see it getting ready to destroy GR. You can also see it conversely. Einstein's genius was, of course, to unify this into G mu nu. But now we are undoing it again. Why there's C squared here is just that we know from Newtonian physics that the Newtonian potential sits in the time-time component of the metric. And then you can start to expand T in powers of 1 over C squared or C squared, depending on what you want to do, and see what happens to the local symmetries and to the geometry and the equations of motions and the actions. Just to say, Marc's beautiful paper was called the zero signature limit of GR, right, if I remember well, and that was precisely because, right, if you send C to 0, then there's no signature here anymore. But it doesn't mean that you lose the time direction, right? Because you see, so what survives here is the leading order component of this. This is precisely my h from the previous transparency. But on the other hand, in the inverse metric, what survives is the leading component of v, and that's the time-like vector field. And in that way, really, in a very nice way, you can get the stuff I showed you before from a large C expansion. But it also shows that you can get covariant objects to any order of C. And so it's actually a very beautiful way to geometrize any post-Newtonian, or for that matter, it's a new buzzword now, post-Carrollian expansion order. And then the underlying symmetries are actually described by a beautiful mathematical tool called the Lie algebra expansion. Okay, I'll skip that. Great, okay, we have 20 minutes for some string theory applications. Yeah, I went a little slower here, but I think it's better to emphasize the important, simple parts. But are there any questions at this point before I up the game a little bit to go to string theory? Okay. So just to give you an idea of non-Lorentzian coordinates in string theory, and I will not so much focus maybe on the results that, of course, in 20 minutes cannot give technical results, but a little bit on the why and how and takeaway, main takeaways. Yes.
Out of curiosity, what sort of question did you ask to get this image?
Yeah, okay, very, very simple. I said, I'm making a slide for a talk with the header non-Lorentzian coordinates in string theory. Can you give me a picture? So the prompt is the title. That's all. That's nice, right? And I did, you know, I could have fiddled with it. I don't like this, but this is very authentic, as authentic as AI can be. Well, thanks for the question. So actually, also historically, well, sometimes you shouldn't give talks historically, but actually the historical way fits kind of with my lecture. So historically, various people, including myself, but also various other groups around the world, started to think sort of 10 years ago, started to revisit non-relativistic string theory. Okay, I should start at the beginning. Non-relativistic string theory was already found in 2000 by Gomisar-Onguri and Danielson and collaborators. Yeah, people of a certain age know these times and other people don't, but okay, this is a while ago. But it was a very exciting time. And it's a limit of string theory that is non-relativistic, and one of the ideas was, okay, that maybe it's just like a little bit according to this Bronstein cube that I gave. Maybe this is a simpler limit where we can understand some features of string theory deeper. And it was actually proven that it's, because one thing is doing a limit, you actually have to convince yourself that it, insofar as you're interested in a theory of quantum gravity, that it's ultraviolet complete. But it's believed to be a self-consistent ultraviolet complete corner. So, just to say, in 2000, non-relativistic string theory was written down in non-relativistic space-time. I mean, people said, this is non-relativistic string theory in flat space-time. I remember reading it, I thought, okay, that's non-relativistic string theory in Minkowski space-time, because that's flat space-time, right? But we never asked the question what kind of flat space-time it was. Maybe from this lecture is now clear, now we know that was non-relativistic strings propagating in a flat Newton-Cartan space-time, not Minkowski. How this became clear is because, okay, that now wind further, 16 years later, 2016 or 15, we started, collaborators of me and some other groups, asking ourselves, interesting, this theory exists. Actually, we had learned a lot about non-relativistic particles moving in Newton-Cartan spacetimes. What's actually the question? What's actually the curved version that non-relativistic strings as found in 2000 probe? That was the question we asked, and we, that turns out to be some other non-Lorentzian spacetime that I will show you some pictures of soon. So that's sort of where this story originates. Then very recently, when you are in the realm of superstring theory, there's a beautiful structure called dualities. Different objects are related between dualities, strings and branes. All this is thanks to supersymmetry. But then once you have something that has to do with strings, then by dualities you can get a corresponding structure, to say in a very infantile way, that has to do with branes. So we started applying these dualities and found like a whole interesting landscape of non-Lorentzian backgrounds in string theory that are related to different so-called decoupling limits. And decoupling limits always have this feature that they sort of simplify the spectrum by zooming into a particular heavy, in particular BPS state. And they are powerful because they often give access to non-perturbative regimes. What's happening in the decoupling limits, I just wanted to give you a schematic understanding here in this picture. It's actually relatively simple if you understand. It's just a direct analog of the non-relativistic limit. Here I repeat for you the computation of the spectrum in the non-relativistic limit of a relativistic particle close to the rest mass. Energy. Now I like to cancel the rest mass contribution. That's why I consider an extremely charged particle in a critical electric field phi. I take now suddenly units, sorry, that Q is mc squared in this critical field. Well, I'll say it different. Q is m and my critical field is c squared. That's my conventions. And that makes the infinity cancel, and then you get the energy above this mc squared. That's your usual non-relativistic spectrum. Zooming in to a BPS state is precisely of this form. Why? Take some BPS state, it has supersymmetry, essentially charge equals mass. This is the heavy state. I call it M1 here. Instead of, so for a relativistic particle, you have the rest mass and the excitations is the momentum around it. For in string theory, given some background BPS state, you can have some other object with little mass m that forms a so-called half BPS state. It's not so important to know, but there are structures in string theory that precisely give the same square root. Now, because this BPS state, the background state, has charge equals mass, I can turn on the electric field again. The charge equals the mass here. I can take the large m limit, and again, there's a cancellation of the infinity, and you get the same structure as this here. So, whenever you scale to a supersymmetric background, you can cancel the divergence with the electric field, and you get a non-relativistic-like spectrum, really of the form something squared divided by the rest mass. Here you see excitation squared divided by the rest mass. This is generic in string theory for half BPS states. And we have many of these interesting BPS states that we can do this to, D-branes and fundamental strings. Then the other thing that's ingredient that to sort of appreciate why string theory gives an interesting generalization and why we need the word non-Lorentzian, and we cannot do any more with here we still have a word that's non. Sorry. This is a particular type of non-Lorentzian geometry that I want to introduce called p-brane Newton-Cartan. In this terminology, the original Newton-Cartan that I showed you is zero brane, particle Newton-Cartan. The way to envision it is this. Start with a flat metric and separate some longitudinal directions, p plus one of them, and some transverse. I work in 10 dimensions for definiteness, but can be in any dimension. So longitudinal transverse. Now, the whole essence of non-Lorentzian limits is you, and that's also embodied in these contractions, you scale up one set of directions and you scale down some other set of directions. For a particle, it's like we scale up time, right? Time becomes more dominant than space. But for a brain-like generalization, we say, let's scale up the longitudinal brain directions and scale down. It's just conventions, by the way. I could also put here omega squared and here 1. But it's the relative scaling that's important. And you scale down the transverse directions. That, now in the limit omega to infinity, gives us a priori a degenerate metric, right? This is not a Riemannian metric, but it defines for us precisely what p-brane Newton-Cartan geometry is. And you can just check for yourself that this has local SO1, p and SO9, p on the transverse space, but a p-brane boost symmetry relating longitudinal and transverse directions. In particular, instead of time being absolute, now the longitudinal space-time coordinates are absolute, and transverse are related by some generalized Galilean boost. This is flat space. You can easily generalize this to curved spacetimes by introducing these vielbeine, now with extra indices. And the whole picture is just a generalization of what I showed you before. You have some metric on the brain and some metric perpendicular to the brain, that incorporates this, but a p-brane Galilean boost relating them. So we don't have any more full 10-dimensional Lorentz invariance. The brain has broken it, and the scaling up and down of transverse and longitudinal has broken it. It's these type of geometries that naturally will appear when you, I will not show you details, but when you implement this limit in string theory. Just like I've shown you how Newton-Cartan naturally appears when I do this limit in ordinary, in general relativity, say. Yeah, okay, then there are various motivations to study non-relativistic string theory. I will not go through all of them, but just to say, because it relates to this Bronstein cube, one of the questions that I found interesting, actually maybe even like connecting to nature, is whether this non-relativistic quantum gravity corner can be made well-defined and embedded in string theory, and maybe, okay, this is very preliminary, but you should always try. Maybe make some, have a framework to make some predictions for low-energy quantum gravity. And there are these days tabletop experiments that can measure gravity at a lower and lower scale, and who knows, in the faraway future we have access to it and can use some of these techniques. Yeah, so I'm going to now skip a little bit because I find it important to stay in time and maybe even stop a little bit before. But just to say, just like how I showed you how to get the coupling of a non-relativistic particle to Newton-Cartan, you can in the same way now find how non-relativistic strings couple to a new version of Newton-Cartan. It's called string Newton-Cartan. That string Newton-Cartan has slightly different features because, yeah, it's basically now a Riemannian geometry fibered over a two-dimensional Lorentzian base, but with Galilean symmetries relating. One more point, and then I jump to the takeaways. Again, I emphasize that it's also interesting to ask what these non-Lorentzian geometries, what's their dynamics. What's very beautiful is, well, in relativistic string theory, we can derive Einstein's equations from consistency conditions, so-called beta functions, on the world sheet. In the same way, in string theory, you can get these non-relativistic dynamical gravity theories from beta functions in non-relativistic strings in curved spacetime. That's very beautiful. Okay, then there's a brain story that I skip. but that essentially I'll summarize in the, in the punchlines here. So that's a lot. In these main takeaways, basically, I'm skipping this part, but I'm saying it in some words. So I think the main takeaways that I hope you go away with is that non-Lorentzian geometry, and concrete versions of that being Newton, Cartan, and Carroll, are controlled degenerations of relativistic symmetry. The metric is replaced by other covariant objects like a clock form, spatial metrics, longitudinal field binding, Newton-Cartan, Carrollienne structures, etc. So I think that's the main takeaway I hope you get from this. And I didn't write it. And that the underlying symmetries are of the type that have been discussed in the first lecture by Professor Henneaux. The other takeaway is that string theory actually naturally generates non-Lorentzian geometries. I indicated it a little bit in passing by saying that these zero branes precisely in the BFSS limit are non-relativistic particles probing Newton-Cartan geometry. I also flashed it with non-relativistic strings probing some other stringy Newton-Cartan geometry. Believe me, it works out for not just deep zero branes and fundamental strings, but for all branes. And they arise in particular in a very natural way, these non-Lorentzian geometries, and near BPS decoupling limits. And one thing that I would highlight also in view of the lecture, algebraic, it's very algebraic, but many people love it, including myself. If you think about it, why this is all very nicely embedded in string theory is because superstring theory has a very big symmetry. It's called the type 2A M-theory superalgebra. And it's sort of a super Barkman, but super Barkman. I mean, there's actually a super Barkman, but this is more super than the super Barkman. But there's a super Barkman in the sense that I showed you a Barkman algebra with one central element. String theory has many, many central elements, and it's precisely this richness of central elements that allows you to take all kinds of interesting Inonu-Wigner contractions, each belonging to a different corner in this duality web. And, okay, that was a whole separate talk maybe that rather surprising, well, in hindsight not. But the non-Lorentzian geometry actually provides an underlying geometry for vanilla ADS-CFT. In fact, the ADS-CFT limit is a non-relativistic limit. But it becomes just very transparent if you formulate it geometrically in this way. So the ADS-CFT limit is really a non-relativistic limit of the D3 brane theory and the bulk theory. Precisely because you can show that the non-relativistic limit in the bulk becomes a near horizon limit. So that's very deep, I think. But that's just a reformulation of known things. Where it becomes interesting is this now gives you a language to find novel generalizations of holography. Because you can do these things multiple times. Or you can take near BPS limits not for half BPS states, but a quarter BPS states. And that already opens up a whole interesting zoo of novel holographic dualities with bulk non-Lorentzian gravity duals. So further developments, this correspondence actually for matrix quantum mechanics that I hinted at is being revisited. Like what can we learn more about matrix theory and BFSS? I mentioned ADS-CFT. We have only scratched the surface of finding actually non-Lorentzian supergravity theories and how we know various candidate solutions of theories we don't know, of actions we don't know. Just because it's technically quite complicated. So there's a bunch of non-Lorentzian supergravities known, like the one for so-called torsional Newton-Cartan strings, but there are many ones still to be done. It actually turns out that this is very fascinating, I can say in one word. The opposite of non-relativistic limits is TT bar deformations. So What's known as a TT bar deformation in string theory is essentially going from the non-relativistic string back to the relativistic string, and also for particles. This was also seen in some papers of TT bar people. But this kind of duality web, well, not only suggests, it gave us the tools to generalize TT bar to higher dimensions, because essentially TT bar in those cases is how you flow from some super Yang-Mills theory back to the full dBi action. So that's quite a nice spin-off. The algebraic aspects I mentioned, then there's something with matrix string theory, and then interesting extensions, tensionless Carrollienne strings, de Sitter, heterotic. You can rewrite 2 volumes of Green, Schwartz, and Witten, and probably duplicate those again. Because, but we're not looking for work, we're looking for interesting problems, so we will not do that. But so just to underscore, just on the, if you're not interested in string theory, I think even on the pure gravity part, there are just as novel covariant tools for limits of GR. I personally think it's interesting and not fully developed, and this I already mentioned, to maybe have the tools to understand non-relativistic quantum gravity better. Then I mentioned this many times. The hope is, for example, to get new insights into big problems like black hole physics, microstate counting, and de Sitter holography. And sort of based on this. It's 31. I should have stopped a minute ago, but I stop hereby. Thanks.